Every detail in this story comes from real scientific research and observation. Tonight, we are going to the moon. Not in imagination alone. Right now, as you listen to this, 4 human beings are aboard a spacecraft called Orion, moving through deep space, farther from Earth than any humans have traveled in more than 50 years. This mission is real. It launched on April 1st, 2026, from Kennedy Space Center in Florida, and tonight on Flight Day 6, those 4 astronauts are completing a lunar flyby, the closest human approach to the moon since Apollo 17 in December of 1972. This channel is brand new, and if what you hear tonight moves you, please consider subscribing, leaving a like, and turning on notifications. It helps more than you know, and it means we can keep making these for you. Just relax, and feel free to let this play as you drift off to sleep. Now, let us begin. Before we go there, let us understand what is happening and why it matters. The Space Launch System rocket that carried the Orion capsule into the sky stands 98 meters tall. It burns approximately 2.7 million kilograms of propellant during its first 2 minutes of flight. When it lifted off the pad at Kennedy Space Center, it generated 8.8 million pounds of thrust, more thrust than any rocket since the Saturn V that carried Apollo astronauts to the moon between 1969 and 1972. Inside the Orion capsule, 4 people are traveling at speeds that exceed 36,000 kilometers per hour during portions of their transit. The moon is roughly 384,400 kilometers from Earth on average. At their trajectory, the crew crosses that distance in approximately 4 days. Tonight, Orion passes within 4,070 miles, about 6,550 kilometers, of the lunar surface, not landing, not orbiting, a free return flyby. The spacecraft uses the moon's gravity to loop around and slingshot back toward Earth. No engine burn required. The physics of orbital mechanics, calculated to extraordinary precision, do the work. And at the moment of greatest distance from Earth, 252,757 miles from home, this crew will have gone farther than any humans in history. That record was held for 56 years by the crew of Apollo 13. Tonight, you are going there with them. You are inside the Orion capsule. It is not a large space. The pressurized volume available to the crew is approximately 8.95 cubic meters, roughly the interior of a mid-size van. 4 people, 10 days, no windows to open, no room to pace. But there is a window. You press your face toward it. Outside, there is nothing and everything. The blackness you see through the glass of that window is not the darkness of a room with the lights off. It is the absence of atmosphere, no air to scatter photons, no dust to soften shadows. The stars do not twinkle out here. They are fixed points of hard white light, burning without wavering, the way stars only appear in the vacuum of space. Each one you can see is a sun. Many of them are suns larger than our own. The nearest one beyond our solar system, Proxima Centauri, is 4.24 light-years away. The light entering your eye from that star left its surface more than 4 years ago. You are moving away from Earth at a speed that makes that distance feel almost mythological. And yet here you are, inside a capsule built by human hands, breathing recycled air, watching the world you were born on grow small in the window behind you. Earth is behind you now. 3 days ago, it filled the window, a disk of blue and white and brown, rotating slowly, cloud systems spiraling across ocean basins the size of continents. You could see the curvature of the atmosphere, that thin blue line at the horizon that separates the biosphere from the vacuum. The atmosphere of Earth, the layer that makes all known life possible, is approximately 100 kilometers thick. The distance from Earth's surface to the edge of space is less than the distance you might drive to visit a friend. Now, Earth is smaller. It has been shrinking at a rate determined by your trajectory and your speed. In the early hours of the mission, it still looked enormous, the largest object in your view, dominating the sky outside the port window. Now it is a circle that fits behind your thumb if you hold your hand up to the glass. You have left home. Not in the way humans have left home before, not a drive away from a familiar city, not a flight across an ocean. You have left the gravitational dominance of the planet where your species evolved. You are moving through cislunar space, the region of space between Earth and the Moon, at a speed that no train, no aircraft, no automobile could ever reach. And the Moon is ahead. The moon you are flying toward is not the moon of mythology or poetry. It is a real object, and its reality is stranger and more remarkable than any legend. The moon formed approximately 4.5 billion years ago, roughly 30 to 50 million years after the formation of the solar system itself. The leading scientific model for its formation is called the giant impact hypothesis. According to this model, a body approximately the size of Mars, designated Theia, collided with the early proto-Earth at an oblique angle. The impact was not a head-on collision, but a glancing blow. The energy released was immense. Temperatures in the impact region reached tens of thousands of degrees Celsius. The material ejected by the impact, rock, mantle material, vaporized crust, was thrown into orbit around Earth. Over a period estimated at perhaps a few thousand to a few million years, that debris coalesced under its own gravity into the body we now call the Moon. This means the Moon is partly made of Earth. The iron-poor composition of the lunar crust, significantly different from the iron-rich material at Earth's core, is consistent with this model. The Moon does not have a substantial metallic core the way Earth does, because the impact debris came primarily from the outer layers of both bodies, not from their interiors. The Moon is 3,474 kilometers in diameter. Its mass is approximately 1.2% of Earth's mass. Its surface gravity is 1.62 meters per second squared, about 1/6 of Earth's. If you stood on the surface of the Moon, you could jump approximately 6 times higher than on Earth. You could throw a rock 6 times farther. Your footprint in the regolith would remain undisturbed for millions of years because there is no wind, no rain, no erosion of any kind on the airless surface. But you cannot stand on it tonight. Tonight, Orion passes by at 4,070 miles above the surface, close enough to see craters with the naked eye, close enough for the crew to make scientific observations that no satellite has ever been able to make, observations that require human eyes, the ability to distinguish color in changing light, to notice something unexpected and describe it in real time to scientists waiting on Earth. The lunar science team at Mission Control has identified approximately 35 geological features for the crew to observe. They work in pairs. One crew member looks through the window and describes what they see. The other records. Mission Control listens. Scientists watching monitors begin updating their models in real time. This is science happening right now. You press closer to the window. The moon is becoming visible not as the disk you see from Earth, round and bright and familiar. Out here, the geometry is different. The moon is beginning to show itself as a sphere, a world, a three-dimensional object with a surface that has texture and relief, light catching the edges of crater rims, shadow pooling in the interiors of ancient basins. The surface beneath you is not smooth. The moon has been struck by impactors for 4.5 billion years. Every crater you see is a record of a collision. Some are small, punched into the regolith by rocks no larger than a fist. Some are ancient basins hundreds of kilometers wide, carved by bodies the size of cities or small moons. Impacts so energetic that they melted the crust and created vast seas of cooled volcanic rock that early astronomers named the Maria, the Latin word for seas. They appeared dark and flat through early telescopes and were mistaken for oceans. They are not water, they are basalt, solidified lava. The largest of the lunar basins, the South Pole Aitken Basin, is approximately 2,500 kilometers in diameter and 8 kilometers deep. It is one of the largest confirmed impact craters in the entire solar system. It formed roughly 4 billion years ago during a period called the Late Heavy Bombardment, a time when the inner solar system was being pelted by debris left over from planetary formation, and the surfaces of the Moon, Mars, Mercury, and early Earth were being carved and reshaped on a massive scale. You are flying over the record of that era. Everything beneath you is a scar, every crater a timestamp. The Moon is the most complete geological archive of the early solar system that we have direct access to, because unlike Earth, the Moon has no plate tectonics, no significant erosion, no weather. What happened 4 billion years ago is still there, waiting, preserved in stone. The crew reports their observations to Mission Control. They are describing color, shades of brown, hints of blue. These subtle differences in reflected light carry information about the mineral composition of the surface, the ratio of olivine to pyroxene, the age of the regolith, the presence of impact melt. Human eyes, trained and attentive, can perceive these variations in ways that satellite cameras, limited by bandwidth and orbital geometry, sometimes cannot. The science team receiving these reports is already synthesizing them, already adjusting their models, already asking follow-up questions. You let your weight settle into the seat. The hum of the ventilation system continues, low and steady. And outside the window, the moon grows larger, slowly, the way a destination reveals itself to a traveler who is almost there. The spacecraft is quiet now. You are in the gradual approach phase. Orion has been flying for 6 days, and the crew has settled into the rhythms of deep space operations. They exercise each day. The capsule includes a resistance device, because in microgravity, without the constant work of supporting the body against Earth's gravity, muscles and bones begin to lose mass within days. The rate of bone mineral density loss in microgravity is approximately 1 to 2% per month. The muscles of the lower back and the legs, those that do the most work resisting gravity on Earth, are among the first to begin adapting to their new, weightless environment. Exercise is the countermeasure. The crew pulls, pedals, works against resistance for about 2 hours each day. Not because it feels necessary in the moment. In microgravity, the body does not feel weak. It feels light, almost effortless. The sensation of weight is simply absent, but that absence is a signal, and the body responds to signals. Without the compressive load of gravity, bones receive no stimulus to maintain their density. Without the constant effort of standing and walking, muscle fibers receive no stimulus to maintain their mass. The body begins quietly and efficiently to lighten itself. The exercise protocol maintains the load. It tells the body, at a cellular level, we still need this. You are floating in your seat, or what feels like floating, the gentle restraint of the harness, the only thing distinguishing sitting from drifting. The cabin air is regulated to a temperature between 18 and 27 degrees Celsius. The pressure is maintained at approximately 101 kilopascals, the same as sea level on Earth. Every breath you take has been cycled through the environmental control system, the carbon dioxide removed by a chemical scrubber called a CDRA, the carbon dioxide removal assembly, which uses a zeolite-based molecular sieve to capture CO2 molecules and vent them overboard. The air is safe. The capsule keeps it safe. You look down at your hands and notice that they drift slightly if you do not hold them against the armrests. Not because of any force. There is no force. It is because there is no weight. In microgravity, the body's fluids shift upward toward the head. Astronauts often describe a sensation of pressure behind the eyes and in the sinuses in the early days of spaceflight, as fluid that normally pools in the lower body redistributes. The face can appear slightly puffy, the legs thin slightly, their fluid migrating toward the torso and head. The body adapts. Within a few days, the shift stabilizes. You feel the quiet of the capsule settle around you. The ventilation fans cycle at low speed. The instruments give off a faint rhythmic sound, not mechanical noise, but the specific electronic hum of systems that are running within their expected parameters. Everything nominal, everything steady. Outside, the moon is 6,500 kilometers below the belly of the spacecraft. 6,500 kilometers of nothing between the hull and the surface. No air, no medium, just vacuum and the geometry of the orbit. You are the farthest you have ever been from Earth. You are the farthest any human has been in 56 years. And somewhere in the dark ahead, a crescent of ancient light is beginning to resolve itself into mountains, into craters, into the surface of another world. You breathe slowly. The moon waits. The stars outside the window do not move. They never move. They are so far away that even at the speed you are traveling, tens of thousands of kilometers per hour, the parallax shift of the distant stars is unmeasurable to the human eye. They appear fixed, eternal, the same stars that the Apollo crew saw from this distance, the same stars that humans have been watching from Earth for 100,000 years, and for the last 56 years, from this very region of space, by no one at all. Until tonight. The moon is close now. Closer than it has been to human eyes since December of 1972, when the crew of Apollo 17 left the surface and began their journey home. That was the last time human beings were this near to another world, 53 years ago. A generation, 2 generations for most of the people alive right now. You look through the window. The surface below is no longer an abstraction. It is a landscape. You can see ridgelines, the long, irregular edges of crater walls, casting shadows that are perfectly sharp because there is no atmosphere to scatter the light, no air to soften edges, no haze to blur the boundary between light and dark. The terminator line, where lunar day meets lunar night, is a razor edge. On one side, bright rock heated by the sun to temperatures reaching 127 degrees Celsius. On the other side, absolute shadow, where temperatures can drop to minus 173 degrees Celsius, a temperature difference of 300 degrees across a few kilometers of surface, with nothing in between. The moon has no atmosphere to speak of. What it has is called an exosphere, a tenuous collection of particles so sparse that they almost never collide with each other. The total mass of the lunar exosphere is estimated at approximately 10 tons. Earth's atmosphere masses roughly 5.15 times 10 to the 18th power kilograms. The difference is not a difference of degree, it is a difference of kind. Without an atmosphere, the moon has no weather, no wind, no rain, no erosion, no sound. If you were standing on that surface right now and a rock broke off a cliff 500 meters away from you, you would see it happen and you would hear nothing. The vibration would travel through the ground, and if you were standing on the surface, you would feel a faint tremor in your boots. But through the air, silence, complete silence. The moon is one of the quietest places in the solar system. You follow the terminator line with your eyes. It runs roughly north-south across the disk below, the boundary between the illuminated near hemisphere and the dark far side. Orion is approaching from the near side, the side that always faces Earth, and will swing around into the far side during the communications blackout phase. There is a crater below you now that you can identify. It is called Orion Tail Basin. Orion Tail is one of the youngest large impact basins on the moon, formed approximately 3.8 billion years ago at the tail end of the late heavy bombardment. It is a multi-ring impact basin, which means that the energy of the impact was large enough not only to excavate a crater, but to send concentric rings of mountain ridges radiating outward from the impact point, like the rings that expand across the surface of water when a stone is dropped into it. The outermost ring of Orion Tal is approximately 930 kilometers in diameter. The mountains at the rim reach heights of several kilometers. The interior basin floor is covered with impact melt, rock that was liquefied by the kinetic energy of the impactor, poured into the basin and solidified into smooth plains of basalt. From space, Orion Tail looks like a bullseye. From where you are now, it looks like an ancient wound in the surface of the moon, and in a sense it is. The impactor that created Orion Tail was moving at perhaps 15 to 20 kilometers per second when it hit. The impact released energy equivalent to billions of nuclear warheads detonating simultaneously. The rock in the impact zone was vaporized, melted, excavated, and thrown hundreds of kilometers in every direction. That happened 3.8 billion years ago. The evidence is still perfectly preserved. You stare at it for a long moment. The crew is describing it to mission control right now, in real time, from a window very similar to the one you are looking through. They are noting the color at the rim, the texture of the melt plains, the way the shadow falls across the secondary craters that ring the basin's exterior, smaller impacts created by debris thrown out from the original strike. Each secondary crater is a piece of evidence. Each one was formed within seconds of the original impact, as Orion Tal's ejecta landed at high velocity across hundreds of kilometers of surrounding terrain. The moon's surface is a record of violence, and also of time, of silence, of patience. 4.5 billion years of waiting. The capsule hums around you. You let your gaze move west of Orion tail, if west means anything at this distance and this angle, to a feature called Hertzsprung Basin. It is older than Orion tail, much older. Where Orion tail is relatively fresh, its rings still sharp and distinct. Hertzsprung has been softened by subsequent impacts. Hundreds of millions of years of smaller strikes have rounded its edges, partially filled its floor, blurred the clarity of its original structure. Hertzsprung Basin is approximately 570 kilometers across. It sits on the far side of the Moon, the side that permanently faces away from Earth, the side that remained unknown to human eyes until October 1959, when the Soviet Luna 3 probe flew past and captured the first photographs. For all of human history, until 1959, nobody knew what was on the other side of the Moon. Let that sit for a moment. Every civilization that ever existed on Earth, every culture that ever looked up at the Moon, named it, worshipped it, navigated by it, wrote poems about it, planted crops by its light, none of them knew what was on the other side. It was simply turned away. The Moon's rotation is synchronized with its orbit, a phenomenon called tidal locking, the result of billions of years of gravitational interaction between the Earth and the Moon, and so the same face always points toward us, and the far side remains hidden. The tidal locking process works like this. In the early history of the Earth-Moon system, the Moon rotated freely like any spinning body, but Earth's gravity raised tidal bulges in the solid rock of the early Moon, elongated distortions of the lunar body pointing toward and away from Earth. These tidal bulges were not perfectly aligned with the Earth-Moon axis because the Moon was rotating. The misalignment created a gravitational torque that gradually slowed the Moon's rotation over millions and billions of years until the rotation period matched the orbital period exactly. At that point, the tidal bulge pointed directly at Earth. There was no more torque, and the rotation stopped changing. This process is called synchronous rotation. It is not unique to the Moon. Many large moons in the solar system are tidally locked to their parent planets. Pluto and its largest moon, Charon, are tidally locked to each other. Both always show the same face to the other. The far side of the Moon is not the dark side. It receives the same amount of sunlight as the near side. It is simply the side we cannot see. And in a few minutes, Orion is going to fly behind it. The communications blackout begins at 6:44 in the evening, Eastern Time. Mission Control in Houston is listening to the crew, tracking their telemetry, monitoring the capsule's systems in real time. Oxygen levels, cabin pressure, battery charge, thermal management, propulsion. At this moment, approximately 380,000 kilometers of signal travel time adds about 1.3 seconds of delay to every transmission. A question asked in Houston takes 1.3 seconds to reach the capsule. The answer takes another 1.3 seconds to return. A normal conversation stretched by the physics of the speed of light. At 6:44 p.m., Orion passes behind the limb of the Moon. The signal disappears. From Mission Control's perspective, the screens go quiet. The stream of telemetry, all those numbers, all those indicators, all that data flowing back from the capsule, stops. Not because anything has failed, because the Moon is in the way. The lunar body, 3,474 kilometers in diameter, physically blocks the radio waves that connect the crew to Earth. This is called a loss of signal, or LOS. It will last approximately 41 minutes. For those 41 minutes, the crew of Orion will be completely alone. No radio contact, no voice from mission control, no data downlink, no uplink, no connection of any kind to the planet where billions of human beings are going about their lives, largely unaware of the 4 people passing behind the moon in a metal capsule slightly larger than a minivan. You feel that. The silence of it. The moon is 3,474 kilometers wide. The signal cannot bend around it. The laws of physics do not allow for exceptions. The crew has been briefed. They have trained for this. They know exactly what is about to happen, and they know exactly what to do during the blackout, and they know that in approximately 41 minutes, the signal will return. And yet, to be behind the moon is to be more isolated than any human being has ever been. Not just far from Earth, isolated from Earth, cut off. The crew cannot call for help. Mission control cannot call them. The communication infrastructure that connects modern humans to each other, the radio towers and satellites and undersea cables and repeater stations that form the nervous system of civilization, none of it reaches behind the moon. You drift. In the silence of the capsule, in the hum of the fans, in the soft click of instruments, you drift. The moon passes beneath you at 6,550 kilometers, close enough at this scale to feel like you could reach down and touch it. From this altitude, the lunar surface extends across the window as a vast curving plain of gray and brown and shadow. You watch it. You watch the ancient craters scroll past, craters whose names most people on Earth have never heard, craters that were there before complex life existed on Earth, craters that formed when the most advanced organisms on Earth were single-celled organisms in a shallow ocean. And then, at 7:02 in the evening, Orion reaches its closest approach. 4,070 miles, 6,549 kilometers. The closest any human spacecraft has come to the lunar surface since Apollo 17 left it in 1972. At 7:07, 5 minutes later, Orion reaches maximum distance from Earth. 252,757 miles. 406,716 kilometers. This is the farthest any human being has ever been from the surface of the planet where the species evolved. The record was previously held by the crew of Apollo 13, Jim Lovell, Jack Swigert, and Fred Hayes, set not as a planned achievement, but as a consequence of emergency. Their free return trajectory around the moon, forced by a crisis aboard their spacecraft, carried them 248,655 miles from Earth. That record stood for 56 years. Tonight, the crew of Artemis II breaks it. The moment is marked. Mission Control prepares a message. The crew, in the brief window before the communications blackout ends, will receive that message and acknowledge it. But right now, they are behind the moon, completely alone. In the quiet of the capsule, you think about what it means to be this far from Earth. If you could look toward Earth right now, if you angled the capsule camera back along your trajectory, you would see a small circle, blue, pale, bright against the black, smaller than the width of your finger held at arm's length. The entire surface area of the planet, where every human being you have ever known was born, lived and went about their lives, all of it fitting behind your thumb. This is the view that changes people. Astronauts have described it repeatedly, across 6 decades of spaceflight. The sensation of seeing Earth from space, not from low Earth orbit, where the planet still fills a significant portion of the sky and you can see continents in detail, but from deep space, where the entire planet is a small disk, produces a shift in perspective that some of them have called the overview effect. The recognition, made visceral rather than intellectual, that the boundaries and divisions on Earth's surface are not visible from space, that the atmosphere is impossibly thin, that the planet is small. Carl Sagan described it in 1990, writing about the Voyager 1 photograph of Earth from 6 billion kilometers away, a photograph in which our planet appears as a pale blue dot less than a pixel across in the image. He wrote that every person who ever lived, every act of kindness and cruelty, every king and farmer, every inventor and explorer, every moment of human civilization had played out on that point of light. From 406,716 kilometers, the Earth is not quite a pale blue dot. It is still a disk, still recognizable, still clearly a world, but the scale of it, the smallness of it, is already beginning to speak. At 7:25 p.m. Eastern Time, Orion emerges from behind the far side of the moon. The mission team has a name for this moment: Earthrise. Not in the literal sense of the famous Apollo 8 photograph, the December 1968 image captured by astronaut William Anders, in which the Earth appears to be rising above the lunar horizon, a blue and white sphere against the black of space. That photograph was taken while Apollo 8 was in lunar orbit. The Earth's apparent rise above the moon's horizon was a result of the spacecraft's orbital motion changing the angle of view. This Earthrise is different. As Orion swings around from the far side and begins the return arc, Earth comes back into view on the opposite edge of the moon from where it disappeared. To the crew floating in the capsule, it appears to emerge from behind the lunar limb, rising, becoming visible, as their trajectory carries them back into contact with home. The signal returns. Mission Control receives telemetry. The screens in Houston come alive again. The voices of the crew crackling slightly across the distance fill the communication loop. 41 minutes. Gone. The crew is back. You exhale slowly. The moon is behind you now, receding slowly, the way a city shrinks when you drive away from it in the dark. Its light, reflected sunlight, the same light that has been illuminating Earth's nights for 4.5 billion years, falls through the window onto your hands. You look at that light. It is old. The photons striking your hands left the surface of the sun approximately 8 minutes and 20 seconds ago. They crossed the inner solar system. They struck the surface of the moon, gray basalt, ancient regolith, the pulverized debris of 4.5 billion years of impacts, and some fraction of them reflected outward, into space, into this window, onto your skin. You're being touched by reflected sunlight that bounced off the surface of another world. That is not a metaphor, that is physics. And in the quiet of the capsule, with the moon growing smaller behind you and Earth growing larger ahead, you let the light rest on your hands. And you rest. The Earth is growing again. Not quickly, not visibly from moment to moment, but the geometry of the return trajectory, the long arc of the free return path, curving back toward the planet under the pull of Earth's gravity, means that every hour, every minute, the distance between Orion and Earth is decreasing. You are coming home. The capsule is oriented so that the heat shield, a disc of Avcoat ablative material 5 meters in diameter, mounted on the blunt base of the Orion crew module, faces forward along the direction of travel, not yet doing its main work. That comes at re-entry, but its orientation matters for thermal management. The spacecraft rotates slowly around its axis during transit, a maneuver called barbecue roll by the early Apollo crews who first used it, and called passive thermal control in the mission documentation. The rotation distributes solar heating evenly across the capsule's surface. Without it, the sun-facing side would absorb heat continuously until materials reach their limits, while the shadowed side would radiate heat into the near-zero temperature of deep space and become extremely cold. The rotation solves this. One full rotation approximately every 20 minutes. A slow, steady spin, imperceptible from inside unless you watch one particular star out the window and count how long it takes to return to the same position. You watch a star, a bright one, near the edge of the window frame. You count. It disappears from view. The capsule turns. The moon, now behind and below, drifts across the glass, then the black, then Earth, smaller than it was an hour ago from maximum distance, but already perceptibly growing. Then the star returns. The universe outside this window is rotating, and you are the still point at the center. The distance back to Earth is approximately 406,000 kilometers as the return arc begins. At the speeds Orion will reach during re-entry, approaching 40,000 kilometers per hour when it hits the upper atmosphere, the crossing of that distance takes approximately 3 days. The crew has 3 more days in this capsule before splashdown. 3 days in a space the size of a mid-size van. The Orion capsule was designed around the ergonomics of the human body in microgravity. The 4 crew seats are positioned around a central display console. The consoles are touchscreen based. Physical buttons have been minimized because in a pressurized spacecraft, physical buttons accumulate wear, can jam or stick, and may behave unpredictably under vibration. The touchscreens allow the interface to be reconfigured for different mission phases. The same screen that shows navigation data during transit can be reconfigured to show life support status, propulsion readouts, communication links, or emergency abort procedures. The crew moves carefully. In microgravity, the concept of moving without touching things is different than on Earth. On Earth, you navigate a room by walking. Your feet contact the floor. Your center of mass shifts. You move. In microgravity, any push against a surface sends you in the opposite direction. The crew must manage Newton's third law constantly. Every motion produces a reaction. Reaching for something floating across the cabin requires a gentle push and a calculated trajectory. Eating, working at a console, sleeping, all of it requires the constant, unconscious recalculation of momentum and position that microgravity imposes. After a few days, this becomes second nature. The astronauts describe it as a kind of fluency, like learning a new language for the body. The first day is disorienting. The vestibular system, designed to interpret signals from the inner ear in the presence of gravity, receives no gravitational signal and becomes confused. Many astronauts experience space motion sickness in the first 24 to 48 hours. Nausea, disorientation, the sensation that the room is moving even when it is still. This typically resolves within 2 or 3 days. By day 6, the crew of Artemis II is fluent. You float in your seat and watch Earth through the window. The planet is a disk, blue predominantly. More than 70% of Earth's surface is ocean, and ocean reflects blue light and absorbs red wavelengths, giving the planet its characteristic color when seen from space. The blue is not uniform. Deep ocean is a deeper, darker blue. Shallow shelf waters near continents are lighter, more turquoise. The difference reflects depth and sediment load. In biology, the phytoplankton populations that live in the upper sunlit layer of the ocean, photosynthesizing, producing oxygen, cycling carbon, forming the base of the marine food web. You can see cloud systems. From this distance, they appear as white swirls against the blue, organized, patterned, the visible expression of atmospheric circulation. The large spiral structures are cyclones or anticyclones, regions of low or high pressure, where air masses rotate due to the Coriolis effect, the deflection of moving air caused by the rotation of the Earth beneath it. In the northern hemisphere, low-pressure systems rotate counterclockwise. In the southern hemisphere, they rotate clockwise. The planet's rotation at a speed of approximately 465 meters per second at the equator imparts this deflection to all large-scale atmospheric motion. You can see a storm system over what appears to be the Pacific. You cannot make out individual waves or coastlines from this distance. The resolution limit of the human eye at 400,000 kilometers does not permit that detail, but you can see the structure of the atmosphere, the way the clouds organize themselves into bands and spirals, the white bright anvil tops of thunderstorms, where convective clouds reach the tropopause and spread laterally, unable to rise further into the stratosphere. From here, the weather on Earth looks slow, peaceful even. From inside it, a hurricane is a wall of wind and water and pressure. From here, it is a white spiral, turning calmly, smaller than your thumbnail. Scale changes everything. The Orion service module, the propulsion and power unit attached to the base of the crew module, is built by the European Space Agency. This is the first time in human spaceflight history that a crewed spacecraft bound for deep space has carried a propulsion system built by a non-American space agency. The European service module is derived from the design of the automated transfer vehicle, the cargo spacecraft that ESA operated to resupply the International Space Station from 2008 to 2015. The service module provides electrical power through 4 solar array wings, each extending outward from the cylindrical body of the module. The solar arrays are positioned to track the sun during the transit, maintaining power generation throughout the mission. Total power output is approximately 11 kilowatts, enough to run the life support system, the avionics, the communication array, the crew displays, and the thermal management system simultaneously. The main engine of the service module is an orbital maneuvering system engine inherited from the Space Shuttle program, a pressure-fed hypergolic engine that burns a combination of monomethyl hydrazine as fuel and nitrogen tetroxide as oxidizer. Hypergolic propellants ignite spontaneously on contact with each other without the need for an ignition spark. This makes them extremely reliable. There is no ignition system that can fail. The trade-off is that both propellants are highly toxic and require careful handling on the ground. In space, they are simply fuel, waiting, stored in tanks in the lower portion of the service module, pressurized and ready. The main engine will not fire for re-entry. Re-entry does not require propulsion. It requires precisely nothing. The spacecraft simply encounters the atmosphere at the right angle, the right speed, and allows physics to do the work. What will happen when Orion hits the upper atmosphere is one of the most precisely violent controlled events in human spaceflight. But that is still 3 days away. Tonight, the capsule is quiet. The crew has completed their observation period. The science data, hundreds of descriptions, thousands of photographs, real-time recordings of color, texture, shadow, and geological feature is being transmitted back to Earth in compressed data packets, sent over the Deep Space Network, received at ground stations distributed across 3 continents, processed and archived, and distributed to the science teams who have been waiting for it. The Lunar Reconnaissance Orbiter has been mapping the Moon's surface since 2009. It has produced the most detailed topographic map of the Moon ever created, but it orbits at 50 kilometers above the surface. It sees the Moon from directly above, with the illumination angle that exists at the time of its overpass. The crew of Artemis II observed the Moon from 6,550 kilometers, a different angle entirely, with different illumination, catching features in oblique light that the orbiter cannot replicate. The oblique view reveals relief. Shadows extend across the terrain at low angles, casting the topography into 3 dimensions in a way that overhead imagery cannot capture. Geologists call this kind of illumination raking light. It is the same principle used by archaeologists and forensic investigators when they suspect a surface has features that are too subtle to see in direct overhead light. You shine the light from the side at a low angle, and the shadows of even millimeter-scale variations become visible. From 6,550 kilometers, at oblique angles, with human eyes that can integrate color and contrast, and subtle tonal shifts in ways that no camera algorithm fully replicates, the crew has seen things no one has seen before. The science team will be working on those observations for years. You close your eyes for a moment. The hum of the capsule surrounds you, the ventilation, the low electronic tick of the instruments, the faint vibration that runs through the structure continuously, not from engines which are silent, but from the thermal management system, the pumps circulating coolant through the radiator panels on the service module. The capsule is alive in the way that engineered systems are alive, not breathing, not thinking, but cycling, processing, maintaining. The thermal control system moves heat from the places it accumulates, the electronics, the crew, the sun-facing surfaces, to the radiator panels, where it is emitted into space as infrared radiation. In space, radiation is the only mechanism by which heat can be transferred to the external environment. Conduction requires contact. Convection requires a fluid medium. In the vacuum of space, there is neither contact nor fluid, only radiation. The capsule radiates heat continuously, and it absorbs heat from the sun, and the thermal management system maintains the balance between the two. You are warm. The temperature in the cabin is approximately 21 degrees Celsius. Your body is generating heat, approximately 80 watts at rest, roughly the heat output of a standard incandescent light bulb. That heat goes into the cabin air, which goes through the environmental control system, which manages it. Every watt your body produces is accounted for. Every breath is measured. Every kilogram of food and water aboard the capsule was calculated before launch, down to the expected consumption rates, the metabolic outputs, the waste management requirements. You exist inside a system that knows you are here. It has accounted for you. Outside, the stars hold their positions. The earth glows, slowly growing. The The moon has diminished to a disk behind you, still large, still bright, but no longer filling the window. You are between worlds. Not on one, not yet on the other. Suspended in the geometry of orbital mechanics, moving along a path that was calculated months before you launched, adjusted by tiny engine burns that measured in seconds, refined by the mathematics of celestial mechanics that Newton first described in 1687, and that has been refined, tested, confirmed, and applied by every mission that has ever flown. The path home was drawn a long time ago. You are following it. And in the quiet of the capsule, between the moon and the earth, you let yourself rest. The universe continues around you, slowly, steadily, without interruption. The crew sleeps. Not all four at once. One crew member maintains watch during each sleep period, monitoring the capsule's systems, staying alert in case mission control sends a communication that requires a response. But 3 of them are sleeping now, zipped into sleeping bags secured to their seats, eye masks blocking the light from the instrument panels, foam earplugs dampening the constant hum of the fans. In microgravity, sleep does not come in the same way it does on Earth. On Earth, the horizontal position of sleep is a response to gravity. Lying down removes the gravitational load from the spine, allows the intervertebral discs to expand slightly, redistributes fluid pressure throughout the body. The horizontal position is not just a preference, it is a physiological adaptation to a gravitational environment. In microgravity, there is no horizontal, there is no up or down. The sleeping bag attached to the seat holds the crew member gently in place, preventing them from drifting. Their spine, freed from gravitational compression, elongates. Astronauts on long-duration missions gain approximately 3 to 5 centimeters in height during spaceflight, not because they are growing, but because the cartilage between vertebrae is no longer compressed. The astronauts often describe their first nights in space as disorienting in a quiet way. The body expects the bed to push back against it. It expects the sensation of weight. Without it, there is a faint uncanniness, a sense that something is missing, that the world is not quite behaving as it should. This is the vestibular system adjusting. The semicircular canals in the inner ear, which detect rotation and linear acceleration, are sending signals that conflict with what the visual system sees. Over days, the brain learns to re-weight these inputs, to trust the eyes more and the vestibular system less, to accept the new normal. Sleep comes. It comes in the same 90-minute cycles of lighter and deeper stages that it does on Earth, because the underlying biology does not change. The brain follows the same electrochemical rhythms it would follow in a bed in Houston or in a sleeping bag in orbit. The environment has changed. The neuroscience has not. Outside the capsule, the radiation environment is something that no person living on Earth's surface can truly experience. Earth's magnetosphere, the region of space dominated by Earth's magnetic field, extends tens of thousands of kilometers into space, deflecting the charged particles of the solar wind away from the planet's surface. At low Earth orbit, where the International Space Station flies at approximately 400 kilometers altitude, the magnetosphere still provides substantial protection. Radiation levels aboard the ISS are elevated compared to Earth's surface, but are manageable for long-duration missions. Cislunar space is different. The magnetic field weakens rapidly with distance. At the distances Artemis II is traveling, hundreds of thousands of kilometers, the magnetospheric protection is essentially absent. The crew is exposed to two primary radiation sources. The first is galactic cosmic rays, high-energy particles originating from outside the solar system, accelerated by supernova explosions, the remnants of massive stars that ended their lives in catastrophic detonations. These particles travel at significant fractions of the speed of light. They carry energies millions of times greater than the particles produced by medical X-ray machines. They cannot be fully blocked by any practical shielding. The most energetic cosmic ray particles can pass through meters of aluminum or water. The only way to reduce the crew's exposure is to minimize the time spent in deep space, which is exactly what the 10-day Artemis II mission is designed to do. The second radiation source is solar energetic particle events, bursts of high-energy protons and heavier ions ejected by the sun during solar flares and coronal mass ejections. These events are less predictable than cosmic rays. A major solar particle event can deliver a biologically significant radiation dose in hours. NASA monitors solar activity continuously during crewed missions. The Orion spacecraft includes a radiation shelter area, a location within the capsule where, in the event of a major solar particle event, the crew can position themselves surrounded by as much material as possible to attenuate the incoming radiation. For this mission, the total radiation dose the crew will accumulate is within acceptable mission limits. But it is real, it is measurable, and it is one of the factors that makes deep space travel fundamentally different from low Earth orbit. Every hour in cislunar space adds to the cumulative dose. The crew carries dosimeters, small instruments that measure and record the radiation each person absorbs. After splashdown, those dosimeters will be analyzed. The data will contribute to the understanding of human radiation exposure in deep space, which is essential for planning the longer missions that will follow. The universe is not empty. It is full of particles moving at nearly the speed of light, carrying the energy of stellar explosions, passing through this capsule and through the bodies inside it, as though the metal walls were barely there. You look out the window. The stars are there, every one of them, the Milky Way, visible as a band of diffuse light crossing the sky, not scattered by atmosphere, not washed out by light pollution, not obscured by clouds, just there. The full structure of the galactic disk, seen from inside it, projected across the sky as a dense concentration of stars in the direction of the galactic center and a sparser distribution in other directions. The galactic center lies in the direction of the constellation Sagittarius, approximately 26,000 light-years away. The light you are seeing from that direction left its sources 26,000 years ago, before the last ice age ended, before the first agricultural civilizations appeared on Earth, when our species was living in small nomadic groups and leaving handprints on cave walls. That light has been traveling since then. It is arriving now, in your eyes. The Milky Way is approximately 100,000 light-years in diameter. The solar system sits roughly 26,000 light-years from the center in the Orion arm, one of several spiral arms that extend outward from the galactic core. The solar system completes one orbit around the galactic center approximately every 225 million years. This orbital period is called a galactic year or a cosmic year. In the roughly 4.6 billion year history of the solar system, it has completed approximately 20 galactic orbits. The last time the solar system was in this same position in the galaxy, the Triassic period was just beginning on Earth. The first dinosaurs were appearing, the first mammals. Since then, 20 laps around the galaxy. You let that number settle. In April of 1970, this same region of space held 3 other people. Jim Lovell, Jack Swigert, and Fred Haise, the crew of Apollo 13, were here at approximately this distance from Earth when an oxygen tank in their service module exploded. The explosion vented oxygen into space, damaging the fuel cells that provided electrical power to the command module. The command module began losing power. Within hours, the crew had to shut it down and transfer to the lunar module, the small 2-person spacecraft designed for landing on the moon, and use it as a lifeboat. The lunar module was designed for 2 people for approximately 2 days. It carried 3 people for 4 days. They had limited power, limited water. The cabin temperature dropped to near 4 degrees Celsius as power conservation measures were implemented. Carbon dioxide levels rose as the lunar module's lithium hydroxide canisters, the chemical scrubbers that remove CO2 from the cabin air, approached their capacity. Engineers on the ground, working with only the materials aboard the spacecraft, improvised a procedure to adapt the command module's square lithium hydroxide canisters to fit the lunar module's round receptacles. Using plastic bags, cardboard from mission checklists, duct tape, and tubing, the crew constructed the adapter. It worked. The only path home was the one already available, the free return trajectory, the same fundamental orbital mechanics that Artemis II is using tonight, which would bring them back around the moon and toward Earth. They had to wait. They waited. Mission Control did not sleep. 3 days later, the crew of Apollo 13 re-entered Earth's atmosphere and splashed down in the Pacific Ocean. All 3 of them alive. The record they set, 248,655 miles, stood because no one went back. 56 years of no one going back, not for lack of desire, not for lack of capability necessarily, though the political and financial will for deep human spaceflight diminished significantly after Apollo ended in 1972. But because the systems needed to do it safely, reliably, repeatedly, were still being built. Tonight, those systems are flying, and the record is broken. Apollo 13 held the horizon for 56 years. Tonight, the horizon moved. The 3 sleeping crew members drift in their bags. The watchkeeper sits at the display console, checking the telemetry readouts, noting the numbers that confirm what the instruments already know. All systems nominal, pressure stable, temperature within range, power generation sufficient, trajectory on track. Nothing requires action. Everything is proceeding as calculated. Outside, the stars continue their fixed, silent positions. The Earth continues its slow growth in the window ahead. The Sun, 150 million kilometers away, continues to pour light and heat across the solar system, illuminating the capsule, reflecting off the white thermal blankets on the exterior, streaming through the windows in bright bands that shift slowly across the interior as the barbecue roll turns the capsule. The watchkeeper makes a note in the log. All normal, all well. The universe turns slowly overhead, the stars wheeling past the window in their long, slow arc. And you breathe. Slow as the stars, still as the dark between them. The 7th day begins the way all days begin in deep space. Not with sunrise, not with the slow brightening of a sky. The sun simply appears in the window, or it does not, depending on the spacecraft's orientation at that moment in its rotation. There is no dawn here, no gradient of light moving across a horizon. There is only the black of space, the fixed stars, and the sun, hard and white and brilliant, a point source of light 150 million kilometers away that casts shadows with absolute sharpness because there is no atmosphere to diffuse it. The crew wakes. Music plays through the cabin speakers, a tradition inherited from the Apollo program, when Mission Control would choose a song to wake each crew member on lunar missions. It was a small gesture designed to soften the strangeness of waking in deep space. It persists in the Artemis program. Today the song is transmitted from Johnson Space Center in Houston, uplinked through the Deep Space Network, converted to a radio signal, sent across the 350,000 kilometer gap between Earth and the capsule, and received by the Orion communication antenna. The signal travels at the speed of light. At 350,000 kilometers, the one-way travel time is approximately 1.17 seconds. The crew hears the music 1.17 seconds after it was transmitted. The delay is too small to notice consciously, but it is there. Every sound from Earth, every voice from Mission Control, every data packet, all of it delayed by the physics of the distance. When the crew speaks to Mission Control, they send a transmission. It takes 1.17 seconds to arrive. The person in Houston hears it, thinks for a moment, responds. Their response takes 1.17 seconds to reach the capsule. The minimum round-trip delay is 2.34 seconds. In practice, with processing time and human reaction, the conversational rhythm has a gap of several seconds between each exchange. This is not telephone latency, this is physics. The Deep Space Network, the infrastructure that makes this communication possible, is a system of large parabolic antenna dishes positioned at 3 locations around the Earth: Goldstone in California, Madrid in Spain, and Canberra in Australia. The 3 locations are spaced roughly 120 degrees of longitude apart, so that as the Earth rotates, at least one station always has line of sight to the spacecraft. The dishes are large. The largest at Goldstone is 70 meters in diameter, because the signals they receive from spacecraft in deep space are extraordinarily faint. The radio signal from Orion, transmitted at approximately 50 watts of power, spreads outward in all directions as it travels. By the time it reaches Earth, that 50 watts has been diluted across a sphere with a surface area proportional to the square of the distance traveled. The power density arriving at the receiving antenna is a tiny fraction of a watt. The 70-meter dish collects every photon from that signal that falls within its aperture and amplifies the resulting current until it can be processed. This is how humanity stays in contact with spacecraft across the solar system. The same principle, large collecting area, sensitive receivers, precise pointing, allows the Deep Space Network to communicate with the Voyager probes, now more than 23 billion kilometers from Earth, transmitting at 23 watts of power and arriving at Earth with signal strength measured in fractions of a femtowatt. A femtowatt is 10 to the negative 15th power of a watt. And it still works. You look through the window. The Earth is noticeably larger than it was yesterday. The return arc of the free return trajectory is not a straight line toward home. It is a long curve, an ellipse whose geometry was set in motion by the translunar injection burn that sent Orion away from Earth 6 days ago, and whose shape was fine-tuned by small correction burns during the outbound journey. the orbital mechanics carry Orion back toward Earth without requiring the main engine to fire. Gravity does the work. The Earth's gravity well, the region of space where Earth's gravitational influence dominates over the moons, begins at a boundary called the L1 Lagrange point in the Earth-Moon system, approximately 323,000 kilometers from Earth. This is where the gravitational pulls of the Earth and Moon balance. Objects at this point feel equal attraction from both bodies and require almost no energy to maintain their position. Orion crossed the L1 point on the outbound journey. Now, on the return, it crosses it again, this time falling toward Earth, accelerating as it descends deeper into Earth's gravity well. Each hour, the gravitational acceleration increases slightly. Each hour, the speed increases slightly. By the time Orion reaches the upper atmosphere, it will be traveling at approximately 11 kilometers per second, about 40,000 kilometers per hour. That velocity must be shed before the crew can safely land. The mechanism for shedding it is the atmosphere itself. But that is still 2 days away. For now, you fall toward Earth in silence, and Earth grows in the window like a light coming on in a dark room. The crew runs through their daily tasks. There is a specific rhythm to operations aboard a crewed spacecraft, a schedule maintained not for its own sake, but because structure in an unusual environment provides cognitive stability. The schedule anchors the day. It gives each crew member a known sequence of activities, a clear sense of what comes next, a framework that prevents the formless drift that unconstrained time in a small capsule might otherwise produce. Morning begins with post-sleep activities, a medical check, blood pressure, heart rate, any symptoms of note, a review of the overnight telemetry, a communication window with mission control to confirm the day's plan. Then breakfast. 189 unique menu items were loaded for this mission. The crew's food was selected months before launch, with input from nutritionists and the crew members themselves. Calorie requirements in space are slightly lower than on Earth for short missions, because the body is not doing the continuous low-level work of standing and walking that burns energy on the ground. But nutritional requirements remain: protein to maintain muscle mass against the atrophying effect of microgravity, calcium for bone density, vitamins, particularly vitamin D, which the body normally synthesizes from sunlight exposure on skin, but which cannot be produced in a pressurized suit under glass that blocks ultraviolet radiation. The food is either rehydratable, freeze-dried, and vacuum-sealed, reconstituted by adding measured amounts of water from the potable water supply, or thermostabilized, meaning it has been heat processed to eliminate microorganisms and packaged in sealed pouches that can be eaten at ambient temperature or warmed in a food warmer. The packaging is designed so that nothing escapes during eating. Droplets of liquid float, crumbs float. In a spacecraft, floating food particles can clog ventilation filters, contaminate instruments, or, if inhaled, pose a respiratory hazard. Everything is sealed until the moment of consumption. Everything is managed. You squeeze a pouch of warm food and watch the way the contents move sluggishly inside the packaging, thicker fluids clinging to the interior walls, moving in slow, low-gravity ways. You take a sip of water from a sealed container with a tube. The water does not flow down by gravity. It is drawn by suction. In microgravity, you do not drink down, you drink in. The workday includes systems checks, science data collection, and in one scheduled window, a live transmission to the public. The crew floats in front of a small camera mounted near the display console and speaks to the world. From their position, Earth is visible through the window behind them, a sphere, turning slowly, filling perhaps a quarter of the frame. The camera captures the capsule interior, the displays, the equipment secured to every available surface with Velcro and bungee cord, the crew in their blue flight suits, moving with the practiced ease of people who have spent a week in this environment and learned its rules. People watching from Earth see their planet through the window. They see it the way the crew sees it, from outside, from distance, from a vantage point that the vast majority of people alive today will never occupy. Something about this image, transmitted across 350,000 kilometers, arrives differently than a photograph. The photograph is static. This is live. The crew is there right now. The planet behind them is there right now. The distance between the screen you are watching and the capsule shown on it is a real physical distance, not a representation of one. The scientist Kelsey Young, who leads the Artemis II lunar science team, has said that the crew's human eyes in those hours of lunar observation gave scientists something no instrument had before: the ability to ask follow-up questions in real time, to redirect attention to an unexpected feature, to say, go back to that ridge and look at the color at the base, and receive a response within seconds. That is not data acquisition. That is exploration. And exploration requires humans to be present. This is why they went. In the afternoon, the crew conducts a suit test. The Orion Crew Survival System suit, the pressure suit the crew wears during launch, re-entry, and any emergency pressure loss scenario, is an evolution of suits used in the space shuttle era. It is not a spacewalk suit. It is designed for internal use only, to protect the crew if the capsule loses pressure. It has a helmet, gloves, boots, a pressure bladder that inflates to maintain the wearer's body at a safe pressure if the surrounding environment depressurizes. The suit weighs approximately 14 kilograms on Earth. In microgravity, it weighs nothing, but it still has the same inertia, the resistance to changes in motion that all objects with mass possess, regardless of gravitational environment. Moving in a suit that masses 14 kilograms requires applying force to change its direction or speed, even in zero gravity. The crew must learn to work with that inertia, to push before they need to move, to plan their movements in advance, to account for the suit's mass when reaching for controls. The pressurization test involves the crew inflating the suit to operational pressure and confirming that mobility is adequate for performing essential capsule functions. Can they reach the abort switch? Can they actuate the manual controls? Can they communicate clearly through the helmet's microphone? Each check is logged. Each result is transmitted to mission control. The data goes into the record, the accumulated body of knowledge about human performance in pressure suits in microgravity environments that will inform the design of future suits, future missions, future procedures. Every test performed today is a gift to the people who will fly after this crew. The light in the capsule changes as the afternoon rotation carries the sun around the hull. Direct sunlight enters the windows at certain angles during the barbecue roll, sweeping across the interior in a slow diagonal, illuminating the equipment, the sleeping bags secured to the seats, the floating checklist that someone has not yet anchored. The checklist rotates lazily in the moving air from the ventilation system, turning end over end in the slow drift that objects in microgravity adopt when disturbed. You watch it turn. There is something specific about the way objects move in microgravity, a slowness and completeness to their rotation that does not occur on Earth, where air resistance and gravity quickly damp out any spin. Here, without either force acting to stop it, the checklist continues its slow rotation indefinitely, or until someone catches it. The physics of angular momentum, a quantity conserved unless acted upon by a torque. The checklist, given an initial rotation by some accidental brush of a hand, will keep rotating until it contacts another surface. In deep space, in a closed capsule that may take a very long time, you watch it turn, slow and complete and unhurried. And the capsule hums, and the Earth grows, and the day continues, marked not by the position of a sun crossing a sky, but by the schedule on the display, the meals consumed, the tasks completed, the slow accumulation of distance covered on the return path home. In, out. The ventilation fans cycle at their low, steady frequency. The stars outside the window hold their positions unchanging. And you rest in the middle of it, suspended, warm, held, halfway between the moon you have seen and the Earth you are returning to, traveling a path that was calculated long before you launched and that will carry you home as surely as the mathematics that describes it. The capsule knows where it is going. And tonight, that is enough. The Earth is large enough now to see its shape clearly. Not the shape of the planet that has been visible for days, a disk against the black, but the shape of what is on it. The large-scale geography is beginning to resolve. You can see when the window is oriented correctly and the sunlight strikes at the right angle, a dark mass that is not ocean, a continent, the Americas, or something that suggests them, the broad, uneven edge of a coastline that has been there for hundreds of millions of years, the product of tectonic forces that moved vast plates of crust across the planetary surface in processes operating at timescales so slow they are essentially incomprehensible in human terms. The North American continent has been in roughly its current position for tens of millions of years. Before that, it was elsewhere. Before that, it was part of a different configuration of land masses entirely. The supercontinent Pangaea, which existed approximately 335 million years ago, contained within it the material that is now North America, Europe, South America, Africa, and the other continents, all joined together, a single landmass surrounded by a single global ocean called Panthalassa. Pangaea began to break apart approximately 175 million years ago. The breakup was driven by convection in the mantle, the slow, heat-driven circulation of the semi-molten rock beneath the crust, which transfers heat from the deep interior of the planet to the surface. Where convection cells rise, they can push the crust apart. Where they sink, they can pull it down into subduction zones, returning crustal material to the mantle. The coastlines you can see from this window were shaped by those forces. Every continent edge, the curve of the Atlantic seaboard, the straight margins of the African coast, is a scar from a break, a record of separation that happened hundreds of millions of years before any human existed to observe it. You look at the edge of North America through the window. It is the edge of a wound that healed. Day 8. Orion is now within approximately 200,000 kilometers of Earth. The gravitational acceleration is noticeably stronger than it was at maximum distance. The spacecraft is moving faster. The return trajectory continues to steepen. The crew begins preparing for re-entry. Re-entry is not a passive event. It is one of the most precisely controlled sequences in the entire mission. The angle at which the spacecraft enters Earth's atmosphere is called the entry flight path angle. For the Orion capsule returning from the Moon, the allowable entry corridor, the range of angles that will result in a safe return, is approximately plus or minus 1.5 degrees. That is a remarkably narrow band. Too shallow an angle, less steep, and the spacecraft skips off the top of the atmosphere like a stone off water. The atmosphere does not slow it enough, and the spacecraft returns to space on a trajectory that may not be recoverable. At lunar return velocities, an entry angle that is too shallow by 2 degrees can result in the spacecraft bouncing out of the atmosphere and continuing into a trajectory that takes it away from Earth with no way to return. Too steep, and the spacecraft plunges into the denser atmosphere at high velocity, the deceleration forces becoming too extreme for the crew to survive, or the heat load exceeding the capacity of the thermal protection system. The corridor between those extremes is 3 degrees wide. At the distances and velocities involved, targeting a 3-degree window requires navigational precision that would have been computationally impossible before the digital age. The trajectory has been tracked continuously since launch. Small correction burns have refined it. The entry angle has been calculated, verified, recalculated, and verified again. The mathematics is exact. The execution must match it. The heat shield is what makes it survivable. The Orion heat shield is the largest of its kind ever flown. It is approximately 5 meters in diameter, wider than the entire interior of the crew module above it. It is made of a material called avcoat, a silica fiber and phenolic resin compound embedded in a honeycomb structure. Avcoat was originally developed for the Apollo program. The Artemis program has used a modernized version, reformulated using current materials and manufacturing processes. When the heat shield contacts the upper atmosphere at 11 kilometers per second, the interaction between the blunt face of the capsule and the air it strikes creates a shock wave. The air in the shock layer is compressed so violently and so rapidly that its temperature rises to approximately 2,760 degrees Celsius, hotter than the melting point of iron, hotter than the surface of many types of stars. This is not primarily friction, it is compression heating. The kinetic energy of the spacecraft is converted into thermal energy in the shock layer. Most of that heat stays in the shock layer, separated from the heat shield surface by a thin layer of gas, but a portion of it conducts and radiates toward the shield. The avcoat absorbs that energy and responds by ablating. Ablation is controlled self-destruction. The outer surface of the avcoat material absorbs heat until it reaches its pyrolysis temperature, the temperature at which it begins to chemically decompose. As it decomposes, it produces gases that flow outward from the surface and form a boundary layer that partially blocks the incoming heat. The material chars. The charred layer insulates the undecomposed material below it. The gases carry energy away from the surface. The heat shield sacrifices itself. By the time the capsule reaches the lower atmosphere and the heating ends, the outer layer of the heat shield will have been partially consumed, charred, eroded, transformed by the energy of re-entry into gases and carbon residue that trail behind the capsule as it decelerates. Underneath the charred layer, the crew is safe. The shield burns, so they do not. The crew conducts their final systems checks. The service module, the cylindrical propulsion and power unit attached to the base of the crew module, will be jettisoned before re-entry. It has served its purpose, providing power, propulsion, and thermal management for the duration of the mission. It is not designed to survive re-entry. When it separates from the crew module, it will follow a slightly different trajectory and burn up in the atmosphere, its components destroyed by the same heating process the crew module is designed to survive. The separation happens at approximately 5,000 kilometers altitude, roughly 20 minutes before the crew module enters the atmosphere. After separation, the crew module is alone, a truncated cone, 5 meters across at the base, approximately 3.3 meters tall, carrying 4 people and the scientific data and biological samples they have accumulated over 10 days in space. Everything else, the service module, the launch system stages that burn during ascent, is gone. What remains is the minimum necessary to bring the crew home. The capsule orients itself heat shield forward. The crew secures themselves in their seats. The restraints that have been loose during the transit, allowing for movement in microgravity, are now tightened. The crew dons their pressure suits, sealing helmets, checking gloves, verifying pressurization. They are preparing for deceleration forces that will reach approximately 4 times Earth's gravity, 4 Gs, during the peak of re-entry. At 4 Gs, a person who weighs 75 kilograms on Earth effectively weighs 300 kilograms. The chest is compressed. Breathing requires deliberate effort against the weight of the rib cage. The blood pools toward the lower body, unless the person is positioned correctly, which in the Orion seats, angled to distribute the deceleration load across the back and thighs rather than the spine, it is. The seat geometry is not aesthetic. It is biomechanical calculation. You feel the capsule settle into its entry attitude. There is a specific quietness that descends in the hours before re-entry. The crew has done everything that can be done in preparation. The trajectory is set. The systems are verified. What comes next is not controlled by human action in real time. It is controlled by the laws of physics, operating on a precisely shaped object, moving at a precise speed through a precisely modeled atmosphere. The crew's role during peak re-entry is to monitor and to intervene only if something fails. Nothing has failed. You sit in the seat and feel the pressure of the harness against your chest, a reminder that gravity exists, that weight exists, that the body has a direction it is supposed to point toward. After more than a week in weightlessness, the sensation is unfamiliar. Not unpleasant, strange, like a language you spoke fluently once and are now hearing again after a long absence. Familiar, but requiring a moment of recalibration before it makes sense again. The body will remember. Within hours of landing, the vestibular system will begin recalibrating to the gravitational field it evolved in. The fluids that shifted upward during spaceflight will gradually redistribute downward again. The muscles that were unloaded will begin carrying load again, cautiously at first because they have lost mass and strength, and the body is careful with systems that have been changed. The bones will resume their normal mineral maintenance cycle in response to compressive loading. The return to Earth is not instantaneous. It is a process of remembering. The body knows where it came from. It simply needs time to return. Outside, Earth is enormous. It no longer fits in the window. The disk has become a world, the curvature of the limb visible at the edges of the frame. the surface below no longer appearing flat but three-dimensional, the horizon a clear curve against the black, clouds spiral, oceans gleam. The sunlit face of the planet fills the view. From here, you can hear nothing from down there, the hundreds of millions of people living their lives on the surface, working, sleeping, eating, grieving, celebrating. None of that sound reaches this capsule. The vacuum of space transmits no acoustic waves. No crowd, no city, no storm is audible from 50,000 kilometers. But the radio is full. Mission Control is in continuous communication now as the capsule descends toward the entry interface. Flight controllers are watching every parameter. The communication loop is busy with technical updates, confirmations, readiness calls. Each system officer reports in sequence. Each one says, "Ready." The capsule says nothing, it simply falls. At the speed it is falling, the entry interface, the altitude at which the atmosphere is dense enough to begin significant deceleration, is less than an hour away. The crew breathe steadily in their suits. The fans cycle. The stars, visible through the side windows at this orientation, are dimming now as the first traces of atmospheric glow begin. Not re-entry heating, not yet, but the faint luminescence of the uppermost atmosphere catching sunlight at the edge of dawn. The sky is beginning. For the first time in 8 days, there is a sky. And somewhere below that sky, below the clouds, below the storm systems and the ocean basins and the continental shelves, there is the coast of California and the recovery ships waiting in the Pacific, and Mission Control in Houston with its screens and its coffee cups and its people who have not fully slept in 10 days. All of them waiting. You breathe. The capsule descends. Slowly, then faster. The sky brightens at the edges, and the long, quiet arc of the journey begins its final turn toward home. The glow begins at the edges. Not a color you would expect, not the orange of a campfire or the red of a sunset. It is a blue-white at first, almost violet, the color of superheated plasma. The air molecules in the shock layer ahead of the heat shield are being stripped of their electrons by the violence of the compression. Individual atoms struck by the blunt face of the capsule at 11 kilometers per second are ionized, their electrons torn away, leaving behind positively charged ions and free electrons in a state of matter that is neither gas nor solid nor liquid. It is plasma. The fourth state of matter, the most common state of matter in the visible universe. The sun is plasma, the stars are plasma, the vast filamentary structures of the cosmic web that connect galaxy clusters across billions of light years are plasma. On Earth, plasma appears briefly in lightning bolts, in the arc of a welding torch, in fluorescent light tubes. It is not common on Earth's surface. It is the normal state of most of the mass in the universe. And right now, a sheath of it surrounds the capsule. The plasma layer is approximately 2 to 3 centimeters thick at its densest. Its temperature in the stagnation region, the point directly ahead of the heat shield where the shock wave is strongest, reaches approximately 2,760 degrees Celsius. The heat shield is absorbing and re-radiating and ablating, sacrificing its outer layers in controlled increments. The char forms, the gases flow outward. The crew inside remains at cabin temperature. The deceleration begins. At first, it is subtle, 1G, the weight of a body on Earth pressing you back into the seat. After 9 days in microgravity, 1G feels substantial. The harness tightens. The seat pushes against your back. Your arms have weight again. Then 2Gs. The pressure across your chest increases. The suit presses against your body. Your hands, resting on the armrests, feel as though they each weigh several kilograms more than they should. Then 3. Then, at peak deceleration, 4Gs. 4 times the weight of everything in your body. Your blood, your organs, your bones, all of it pressed toward the back of the seat with 4 times the force of Earth's gravity. The seat is angled to distribute this load across your back, your thighs, the base of your spine, not down through your vertebrae, which could compress and injure, but spread across a broad surface, the way engineers designed it after decades of studying what the human body can tolerate and in what configuration. Breathing requires effort. Each breath in, you work against the weight of your own chest wall. You breathe deliberately, controlled. The pressure suit assists. It maintains pressure around the body, preventing blood from pooling too aggressively in the lower extremities, helping maintain blood pressure to the brain. You breathe in, you breathe out. The G load peaks and holds. Outside the windows, the plasma is brilliant, a sheath of ionized light surrounding the capsule, trailing behind it in a luminous cone, visible from the ground below as a streak of fire crossing the sky. From inside, the glow through the side windows casts a moving orange-violet light across the interior. For approximately 6 minutes, the peak heating phase continues. 6 minutes. Then, slowly, it begins to subside. During re-entry, the capsule is in a communications blackout. The same plasma that glows outside the windows is also opaque to radio waves. The free electrons in the plasma layer absorb and scatter electromagnetic radiation at the frequencies used for communication. The signal from the capsule cannot penetrate the plasma sheath. The signal from mission control cannot penetrate it either. For approximately 4 minutes, the crew is again out of contact. Not behind the moon this time, not in the far reaches of cislunar space, in the atmosphere of Earth, 60 kilometers above the surface, surrounded by the plasma of re-entry, separated from mission control by a layer of ionized gas a few centimeters thick. Mission control listens to static. The trajectory is computed, the physics is known, the blackout is expected. The flight controllers watch the clock and wait, the same way every mission control team has waited through every re-entry blackout since the first crewed capsules came home in the early 1960s. When the blackout ends, either the capsule reestablishes communication or it does not. Every person in that room knows both possibilities. They wait, as they always have, as they always will. The signal returns, a burst of static, then a voice, the capsule communicator calling the crew, and the crew responding. All 4 crew members, all systems nominal. The heat shield has performed. The deceleration is within expected parameters. The capsule is intact. The room exhales. The plasma has dissipated. The capsule is now below 45 kilometers altitude, decelerating through progressively denser atmosphere. The deceleration forces have eased from 4 Gs back toward 1, but gravity is still there. No longer the simulated gravity of deceleration, but the real, constant gravity of Earth, pulling the capsule downward at 9.8 meters per second squared, accelerating it toward the ocean below. At approximately 7.6 kilometers altitude, the forward bay cover, a cap protecting the parachute system at the top of the capsule, jettisons. 2 drogue parachutes deploy. Each drogue is approximately 7 meters in diameter. They are not the final parachutes. Their purpose is to stabilize the capsule, to stop the tumbling that can develop as an aerodynamically blunt object falls through dense air, and to begin the deceleration sequence that will slow the capsule enough for the main parachutes to deploy without tearing apart. The drogues snap open. The capsule jerks, the downward velocity decreases sharply, and the sensation is of being pulled upward against the seat restraints. The deceleration spike is brief but sharp. The capsule swings beneath the drogues, stabilizing, the oscillation dampening as the drogues do their work. At approximately 3 kilometers altitude, the drogues are released. 3 pilot parachutes deploy, small and fast. Their purpose is to pull out the main parachutes packed in the compartments behind them. The pilot chutes catch the air and drag the main canopies out. 3 main parachutes, each approximately 35 meters in diameter, unfurl above the capsule. The deceleration is significant. The capsule, which has been falling at approximately 130 meters per second under the drogues, slows to approximately 8.9 meters per second under the mains. 8.9 meters per second is still fast, faster than most people run, but it is survivable for a capsule designed to absorb the impact, with seats engineered to compress and cushion on contact with water. You look upward through the capsule window. The 3 main parachutes are spread wide. Each one is red and white, the colors chosen for visibility against sky and ocean. Each one is 35 meters across. The combined canopy area of the 3 parachutes is approximately 2,880 square meters. Below you, the Pacific Ocean is visible. Gray-blue in the late afternoon light, the swells are visible, not large, not calm, somewhere in between, the ocean surface textured by wind and current. The recovery ships are down there. You can see them from this altitude, small shapes on the water, positioned where the trajectory calculations predicted the capsule would come down. The USS John P. Murtha, the Navy vessel that will retrieve the crew, recovery helicopters, already airborne, flying holding patterns, waiting. The last few hundred meters pass quickly. The ocean rises toward you. Splashdown. The impact is sharp and sudden, a jolt that compresses through the seat, through the suit, through the body. Water rises around the windows on all sides, white foam churning against the glass. The capsule bobs, tilts. The water is not flat. The ocean swells catch the base of the capsule and push it sideways, and for a moment the view through every window is alternating sky and water as the capsule rolls. Then the flotation system activates. Airbags deployed around the base of the capsule inflate and right it, pushing it to its stable floating position with the heat shield down and the crew upright. The motion settles. The capsule rocks gently on the surface. Outside, the ocean. Blue water, real water, not recycled, not contained in a sealed pouch, not managed by an engineering system. The actual Pacific Ocean, stretching to the horizon in every direction, the surface broken by swells that have traveled thousands of kilometers from weather systems far to the west. The crew can hear it. For the first time in 10 days, they can hear something outside the capsule that is not equipment. The ocean makes a sound against the hull, a low, irregular percussion, water contacting metal, the capsule rocking, the swells passing under the base. It is not loud, but it is real. The world is outside the walls again. The recovery team reaches the capsule within minutes. Divers from the USS John P. Murtha approach in a recovery boat, attach a sea anchor to stabilize the capsule against the swell, begin the hatch opening sequence. The hatch seal, which has maintained an internal pressure of 101 kilopascals against the vacuum of space for 10 days, is released. The hatch opens. Air enters. Real air, Pacific air, carrying salt and humidity and the specific scent of open ocean, the combination of dimethyl sulfide produced by marine phytoplankton, sea spray aerosols, the trace gases of a living ocean ecosystem. The smell is unlike the filtered, recycled air of the capsule. It is not necessarily cleaner, but it is different. It is from outside. The crew breathes it. They have been breathing processed air for 10 days. The sudden presence of outside air in the capsule is immediately perceptible, not because the air quality is dramatically different, but because the sensory difference is significant. The human nose can detect dimethyl sulfide at concentrations as low as a few parts per trillion. The smell of the ocean is one of the first signals that Earth is real again, that they are back. One by one, the crew is transferred from the capsule to the recovery boat because the post-spaceflight body is not yet ready to stand and walk. After 10 days in microgravity, the cardiovascular system has adapted to the absence of gravitational stress. The heart does not need to pump blood upward against gravity, and it has partially deconditioned. The orthostatic response, the reflex that maintains blood pressure when a person stands upright, has weakened. If the crew stood up and walked off the capsule, they would likely be dizzy, their blood pressure dropping, as their cardiovascular systems failed to compensate fast enough for the sudden gravitational load. They are carried, not as a metaphor, literally, transferred by sling to the recovery helicopter, flown to the ship, carried to the medical bay. The body is returning. It will take days. Some systems, the vestibular recalibration, the fluid redistribution, happen within hours. The muscle and bone recovery takes weeks to months, depending on how well the in-mission exercise protocol maintained them. The immune system, which behaves differently in space, with certain immune cell populations suppressed and others dysregulated, returns to normal function gradually after landing. The crew will spend the first night aboard the ship in the medical bay, monitored, blood drawn, heart rate tracked, blood pressure recorded in lying, sitting, and standing positions to assess cardiovascular recovery. All of this data will be collected, archived, and added to the growing body of knowledge about human physiology in deep space. Every measurement taken from these 4 people over the coming days and weeks is a data point that will help keep the next crew safer. The mission is over. The science is not. The Pacific is calm now, or calm enough. The capsule floats on the surface, hatch open, its 10-day journey complete. The heat shield on its base is charred, dark, ablated, partially consumed by the 2 760-degree plasma of re-entry, doing exactly what it was designed to do. The outer surface of the thermal protection system is gone in places, sacrificed to the atmosphere. What remains is the record of that sacrifice. Above the Pacific, the sky is blue. Not the hard, black, airless sky outside the windows of the capsule for the last 10 days. A real sky, scattered blue light, the result of Rayleigh scattering, the preferential scattering of short-wavelength blue photons by atmospheric nitrogen and oxygen molecules that occurs throughout the depth of the atmosphere. The sky is blue because the atmosphere is there, because the planet has held onto its air for 4.5 billion years, because the geological and biological processes that maintain the atmospheric composition, carbon cycling, nitrogen cycling, the oxygen produced by photosynthesis, have continued without interruption for billions of years. The sky is blue because Earth is alive. The capsule rocks on the ocean, and the crew of Artemis II is home. The data is already traveling. Before the capsule had fully settled on the ocean surface, before the recovery divers had reached the hatch, the telemetry systems aboard Orion were transmitting, the Deep Space Network stations were receiving, the servers at Johnson Space Center were archiving. The 10 days of mission data, system performance logs, crew biometric records, radiation dosimetry readings, food consumption data, manual piloting performance metrics, structural load measurements from re-entry, heat shield temperature profiles, all of it flowing through the network, being stored, being processed, being distributed to the teams who built each system and who now need to understand how it performed. Engineering data does not wait for the crew to land. It is already being analyzed. And somewhere in that data stream, embedded in files that will be reviewed over the coming months and years, is the information that will make the next mission safer. The 4 crew members are aboard the USS John P. Murtha. Reed Wiseman, Victor Glover, Christina Cook, Jeremy Hansen. They are lying in hospital beds in the ship's medical bay, wearing light hospital gowns, attached to monitoring equipment, blood pressure cuffs on their arms, pulse oximeters on their fingers, intravenous lines for fluid replacement. The body loses fluid volume during spaceflight as the redistribution of fluids toward the head triggers the kidneys to interpret the elevated head pressure as excess fluid and begin excreting it. The crew lands slightly dehydrated as a result. Fluid replacement begins immediately. The gravity they are lying in is the same gravity that has existed on the surface of this planet for 4.5 billion years. It is not new, it is not special. It is the same gravitational field produced by the mass of the Earth, operating at the same 9.8 meters per second squared that it has always operated at. But to bodies that have not felt it in 10 days, it is extraordinary. Christina Koch has been to space before. She held the record for the longest single spaceflight by a woman, 328 consecutive days aboard the International Space Station, before that record was exceeded. She knows what the return to gravity feels like. She knows the weight of her own head on the pillow. She knows the way the mattress pushes back against her back. She knows that within days, the dizziness will ease and the muscles will begin to remember. She has done this before. But this return is different. She has been farther from Earth than any woman in history, farther than any human in 56 years. She passed within 6,550 kilometers of the surface that humans have been staring at since before language existed. She looked at it from a window and described what she saw, and those descriptions will contribute to the scientific understanding of the moon for years. She lies in the medical bay and listens to the ship. The engines of the USS John P. Murtha are a low vibration through the hull. The ocean moves the ship in long, slow swells. The air conditioning hums. Somewhere down the corridor, a door opens and closes. Normal sounds, Earth sounds. The world is full of sound again. In Houston, in the mission control room at Johnson Space Center, the flight controllers are completing their post-mission procedures. The room that has been staffed continuously for 10 days, 3 rotating shifts, each team handing off to the next every 8 hours, the displays never going dark, the communication loops never going silent, is beginning to wind down, not empty, not silent, but the particular intensity of an active deep space crewed mission, the alertness, the readiness to respond, the weight of knowing that 4 people's lives depend in part on the accuracy of your work, is beginning to release. The flight director will close out the mission log. The telemetry feeds will be archived. The consoles will be reconfigured for the next mission. Because there will be a next mission. Artemis II is a test flight. Its purpose, stated explicitly in the mission documentation, is to verify that the Orion spacecraft's life support systems can sustain a human crew in deep space, that the systems and operations essential to a crewed lunar campaign work as designed, that the hardware performs within specifications in the actual flight environment. It has done these things. The life support system maintained breathable air for 10 days. The thermal management system kept the cabin habitable throughout. The crew survival suits pressurized and sealed correctly. The manual piloting tests demonstrated that the spacecraft could be controlled by the crew in the event of automated system failures. The communication systems functioned at lunar distances. The heat shield performed during the highest velocity crewed re-entry since the Apollo era. Every verified parameter is a cleared requirement for what comes next. What comes next is Artemis III. Artemis III will attempt to land humans on the moon. Not a flyby, not a test flight, a landing on the lunar South Pole in a region where permanently shadowed craters have been confirmed by the Lunar Reconnaissance Orbiter and other instruments to contain water ice. Ice that has been there in the permanent shadow of crater walls that have not seen direct sunlight in billions of years, preserved by the extreme cold. Temperatures in the permanently shadowed regions of the lunar South Pole can drop below -200 degrees Celsius. Water ice on the moon is not simply a scientific curiosity, it is infrastructure. Water can be split into hydrogen and oxygen using electrical power, a process called electrolysis. Hydrogen and oxygen are the propellants used in some of the most efficient rocket engines ever built. The ability to produce rocket propellant from resources already present on the moon without having to launch every kilogram from Earth, fighting against Earth's gravity well at enormous energetic cost, changes the mathematics of deep space exploration fundamentally. The ice at the lunar South Pole has been there for billions of years. It arrived, most likely, as a component of comets and water-bearing asteroids that impacted the moon over geological time. These impactors carried water ice in their interiors, water that formed in the outer solar system, where temperatures are cold enough for water molecules to freeze onto dust particles and aggregate into the icy bodies that populate the outer solar system. When those bodies struck the moon, their water was released. Most of it was lost, vaporized by the impact, ejected from the lunar exosphere, but some of it migrated over millions of years in a process called cold trapping, water molecules bouncing across the surface in brief hops during the lunar day, eventually finding their way into permanently shadowed regions where the temperature was too cold for them to escape, where they accumulated over hundreds of millions of years into the deposits that exist today. The crew of Artemis II will be the first humans to stand in those regions. The first humans to see what no human has ever seen. The first footprints in regolith that has not been disturbed in 4.5 billion years. And the data gathered by the crew of Artemis II, the verified systems, the confirmed performance margins, the resolved technical questions, is what makes that possible. Artemis II cleared the path. Artemis III will walk it. The ship moves through the Pacific. The recovery vessel is making its way towards San Diego, where the crew will transfer to aircraft and fly to Johnson Space Center in Houston. The ocean is dark now. Night has come to the eastern Pacific, the sun having set while the recovery operations were still underway. Above the ship, the stars are out. Not as the crew saw them from the capsule, not the hard, fixed points of light against absolute black, undimmed by any atmosphere. These stars are the stars of the Earth's surface, softened slightly by the air. The brightest ones still clearly visible, but the fainter ones lost in the scattered glow of the upper atmosphere. The Milky Way is barely perceptible from the ship, not because it has changed, but because even the modest light pollution of a Navy vessel at sea is enough to wash out the faint outer arms of the galaxy. But the moon is visible. Low on the horizon, a waxing crescent, the same moon the crew flew past 2 days ago, now showing its illuminated edge to the Earth as the angle between the sun, moon, and Earth changes with the moon's orbital progress. The lunar month, the period from new moon to new moon, is approximately 29.5 days. The moon orbits Earth at an average speed of approximately 1.02 kilometers per second, at an average distance of 384,400 kilometers. 4 crew members 2 days ago were 6,550 kilometers from its surface. Now they are lying in a medical bay, listening to the ocean, and the moon is a crescent on the horizon. The same moon, different view. The mission lasted 10 days. From launch on April 1st, 2026, to splashdown on April 10th, 2026. 10 days measured in human terms, in meals eaten, in sleep cycles completed, in communication windows with mission control, in tests performed and data collected, and records broken. In cosmic terms, 10 days is a duration that does not register. The moon has existed for 4.5 billion years. The solar system has existed for 4.6 billion years. The universe has existed for approximately 13.8 billion years. 10 days against those scales is not a rounding error. It is below the resolution of any measurement applied at those scales. And yet, 10 days was enough. 10 days was enough to carry 4 people to the moon and back, to break a 56-year record, to make hundreds of scientific observations of geological features that no human eye had ever seen at that distance and illumination, to verify the systems that will carry the next crew, and the crew after that, and the crew after that. The universe does not need humans to go to the moon. The moon was there before humans existed. It will be there long after. The permanently shadowed craters at the South Pole have been accumulating ice for billions of years without anyone to observe them. But humans went anyway. Because the capacity to go, to build the systems, to train the people, to calculate the trajectory, to verify the physics, to do the work required to send 4 people to another world and bring them back alive, is itself a kind of answer to a question. What are we capable of? This? We are capable of this. You are not on that ship. You are here, wherever here is, in a room, in a bed, in the dark. But for the last several hours, you have been somewhere else. You have been in the capsule, watching Earth shrink in the window. You have been above the craters of the moon, looking at geological features that formed before complex life existed on Earth. You have felt the weight of 4 Gs during re-entry, and the jolt of splashdown, and the smell of Pacific air entering the hatch. All of that was real. The mission is real, the science is real. The 4 people aboard Orion are real, and they are aboard a recovery ship right now, being monitored by doctors, listening to the ocean through the hull of a Navy vessel, beginning the slow process of returning to the gravity they were born in. Artemis II happened. It is happening right now, in the sense that all its consequences, the data flowing into servers in Houston, the crew recovering in the medical bay, the parachutes being retrieved from the Pacific, the capsule being lifted from the water by the recovery crane, are unfolding in real time on the same planet where you are lying right now. The universe is very large, and yet tonight, 4 human beings crossed a small portion of it and came back. And you were there. Let the science settle around you now, like the quiet it always was. The moon is out there, 384,400 kilometers away on average, moving at 1.02 kilometers per second in its orbit, its permanently shadowed craters cold and patient and ancient. The stars are out there, each one a sun, most of them older than ours, many of them surrounded by planets we have not yet seen. The Pacific is out there, 3 square kilometers of ocean for every person alive, full of organisms that have never been named, cycling carbon and oxygen and nitrogen in processes that have been running since before animals existed. The Orion capsule is floating on that Pacific right now. The crew is safe. The mission is complete. And the next one is already being planned. You breathe slowly. The room around you is quiet. The gravity that holds you to your bed is the same gravity that shaped the solar system, that pulled the debris of the giant impact into the sphere of the moon, that keeps the atmosphere pressed against Earth's surface so that the sky is blue and the ocean stays and life continues. You are held by the same force that holds the moon in its orbit. In, out. The universe continues. Slowly, steadily. The stars turn overhead as they have for 13.8 billion years. The moon moves along its arc as it has for 4.5 billion years. And you rest. If you found something worth keeping in tonight's story, this channel would be grateful for a subscription, a like, and a notification turned on. Every one of those small things helps more science reach more people in the quiet hours. The next episode is already waiting. Until then, everything you heard tonight is real. Artemis II is out there right now. Those 4 people made it home. Good night.